Hello everybody, this is Mr. Shaban. Today we're going to complete the lesson of nature of matter. The nature of matter, we have spoken about the differences between solid, liquid and gases in terms of the distance, arrangement, movement, shape, volume and intermolecular force. Then we have spoken about how to change between the different states of matter, how to change between solid to liquid, liquid to gas. And then we have spoken about the exceptions of this process, which is sublimation and deposition. We said sublimation is when you change solid directly to gas. Deposition is when you change the gas directly to solid without passing by the liquid. And then we have spoken about the heating curve. We said where exactly can you find the solid, which is between A and B, liquid between C and D, gas between E and F. And then we have spoken about the differences between the temperatures at different parts of the heating curve. And then we have spoken about the melting point and boiling point. And then we have discussed how the substance can be solid, liquid and gas at room temperature when it comes to melting point and boiling point. And then we have reviewed the cooling curve. Right now we're going to talk about pure substance and impure substance. See guys, the melting point and boiling point act as a fingerprint for a substance. In order to differentiate between every substance, you need to look at the melting point and boiling point. Each substance should have a fixed temperature of melting point and a fixed temperature of boiling point. This fixed temperature is what differentiates between a substance and another. So in the pure substance we have no particles. We have no particles of the other substance mixed with it. Okay, as an example, we have the tap water. Tap water is full of minerals and different particles like calcium ion and chloride ion, while in the other hand distilled water has much purity percentage than the tap water, as the amount of dissolved substance is considered to be less than what we have in the tap water. And then right now we're going to test the purity of a substance. See guys, as I told you, when we have a pure substance, the substance should have a certain melting point and a certain boiling point. So a pure substance has a definite sharp melting point and boiling point. It needs to be one value, it needs to be sharp, it needs to be clear. That's a pure substance. If we have impurities with the substance, we're going to have two different things. The first one, the melting point will fall down and the boiling point will increases. The second one, it melts and boils over a range of temperature. It's not going to be sharp, but it's going to be a range of temperature. Let me discuss with you one of the examples to understand how the melting point, boiling point changes when we find impurities with a substance. We all know that the melting point of an ice is 0 degrees, boiling point is 100 degrees. Have you ever wondered why in Europe, especially during winter, they tend to put salt on the ground? Think about it from a melting point and boiling point of view. During the winter, when the rain falls, temperature decreases over there, so they tend to put salt in order to make the water impure. When they make the water impure, as we have known, that the melting point is going to fall down. So instead of the water changing into ice at a 0 degrees Celsius, it's going to be less than 0. So water will be changing into ice at -5, -4. This gives them the opportunity to not accumulate ice on the street, because they decreases the temperature where the water will change into ice. By doing so, they are going to reduce the amount of money which will be spending on the streets in order to clear the ice from. So melting point decreases when you have impurities, and the more the impurities which is found, the larger the drop will be and the higher the increase will be in the boiling point. Not only that, but you're going to have a wider range. So as you increase the amount of impurities, you're going to have a bigger the chance in the change, in the melting point and boiling point, and you're going to have wider temperature range over which melting and boiling point occur. So that's why over there they tend to put the salt on the street, so when it mixed with the rain, it's going to make an impure water, and the impure water will freezes, will change into ice at a very, very lower temperature than the normal, which is 0. Okay, a physical test of water, it can be the boiling point to check if the water boils at 100 degrees Celsius. This means that the water is pure substance. Then we're going to talk about kinetic theory of matter. Kinetic theory of matter, kinetic means movement. Okay, so we're going to look at the movement of matter. See, kinetic theory states that all matter is made up of particles. These particles vibrate with solids having the smallest amount of vibration, because particles are stuck together and they are not moving freely, to moving freely with a higher speed at a gas, because gas particles have more energy, so the particles move faster in a random position, in random movements. As materials are cooled, the particle's vibration decreases as the particle vibrate less. This means that they have taken the energy out of the particle through the cooling process. Evidence for kinetic theory, we have diffusion. Diffusion can be considered the first evidence for kinetic theory, and I'm going to give you an example to understand diffusion in a better way. I want you to think about the perfume. When we use a perfume in one room, the perfume might be smelly and another person can smell it in another room, right? Perfect. Not only that, but also the air freshener. When we use an air freshener in one room, the perfume or the fragrance of the air freshener spread across the other rooms. So this can state that the particle have diffused. The particle have diffused. So let's discuss diffusion from a scientific point of view. Diffusion is a spontaneous migration of substance from regions where the concentration is high to regions where their concentration is low. So in this process, we're going to find the movement from a higher concentrated area to a lower concentrated area. So over here, this is the high concentrated and this is the low concentrated. High concentrated will be the place where you have used the fragrance. Lower concentrated, this is going to be the place where the fragrance went to. The diffusion will stop when both areas have the same concentration. You should keep this in mind, that the diffusion will stop when both areas have the same concentration of the particle. Diffusion is used as an evidence of the particle theory because gas can be shown to diffuse at a much faster rate than diffusion in liquid. Can you please give me a reason behind that? Think about a reason why the diffusion in gas takes place much faster than in liquid, and why in solid we have no diffusion at all. I think you got the answer correct. The diffusion takes place faster in gas because particles in gas are moving very, very fast when it's compared with the liquid and the solid. While on the other hand, it's a little bit slower in liquid because the particles of the liquid are moving slowly. They slide over each other, so diffusion takes place slower in liquid than in gas. While in solids, we have no diffusion at all because the particles cannot move. The particles only vibrate, and this can give no property for the particle to move from one place into another. Let's double check the Brownian motion. Brownian motion is the movement of particle. Let me give you a story based on the Brownian motion. The Brownian motion is based on or named after a scientist. This scientist was examining the pollen grains under a microscope. He has found that the pollen grains are moving randomly. Then this guy wondered, he said, why are these pollen grains moving under the microscope? They might be a living thing, so they are moving. Then he thought, why don't I change the pollen grains, because they came from a living thing and they are able to move. That's what he concluded, with a non-living thing. So he has replaced the pollen grains with dust particles. So the dust particles are particles that have no movement as per his conclusion, so they are not going to move. When he placed the dust particle in the water underneath the microscope, he has found that the dust particles are moving. Then he said, wait a minute, if I have placed the dust particle, which are non-living things, and I have placed the pollen grain, which are living things, both together in the water, both were moving. So this means that they are not the ones who are moving, but he concluded that the water particles where the pollen grain was in, or where the dust was in, are the reason why these particles are moving. The water particles are hitting the pollen grains and the dust particles in a random movement that causes the appearance of the pollen grain, the movement of pollen grain and the movement of the dust particle. So Brownian has stated that the particles are moving of the water, and because the particles of water are moving, the pollen grain will appear to move from one place into another, and the dust will appear to move from one place to another. So that was the Brownian motion. It's how the water particles will move randomly, as you can see, as per the arrows, and collide with each other and collide with the wall of the container. Let's discuss diffusion in liquids and fluids. When potassium manganate KMnO4 crystals is placed in a warm water, it diffuses. Potassium manganate, by the way, it's a purple color. So when you place a potassium manganate, which is purple, in a warm water, the purple color will diffuses much faster than placing the potassium manganate in a colder water. In cold water, diffusion will take place, yes, but the diffusion will be much slower than the warm water. If you're going to think behind that, you're going to realize that in warm water, the particles have higher energy. As the particles have higher energy, they tend to move faster and they tend to collide harder, and this will cause higher diffusion. On the other hand, when particles are having less energy, they move they move much slowly, and the diffusion is going to be a little bit lower. So respectively are compared, it's shown that the KMnO4 diffuses considerably faster in the warm water. This supports the kinetic theory in that the warmer particles have more energy, so they can diffuse faster. On the other hand, in gases, gases are the diffusion in gases is going to take place much faster than the water. Right now, I'm going to give you an example for the diffusion in gases through this example. This example come frequently in the past papers. So here we have a diffusion tube. It has two opening parts, and it's locked by this cork. So we get one cotton, we soak this cotton in concentrated HCl, and we get this cotton, we put it in concentrated ammonia. When we put the cotton in concentrated ammonia and concentrated HCl, we place each one in one side, and they have found that the fumes that comes out of the cotton moves in this way, and the fumes when it comes from the ammonia moves in the other way. Okay? They have found that when both fumes meet each other, they produce a white ring which is called NH4Cl, or ammonium chloride. But they have found a strange thing. They have found that the ammonium chloride is made next to the HCl. It's away from the ammonia. Then they went to calculate the mass of each molecule. They have found that the mass of NH3 is much lower than the mass of HCl, and we're going to know how to calculate the mass later on in a different chapter. So they have found that NH3 is much lighter than HCl. That's what makes the NH3 travel much faster, and as it travels faster, it's going to cover a large distance. So both are going to meet closer to the HCl, because the HCl particle is very heavy and is going to move slowly, while the ammonia is much lighter and is going to move faster. So they are going to meet each other at this particular spot. So this particular spot where the NH3 is going to meet HCl to form NH4Cl, which is the white ring. So the movement, this question when it comes is going to ask you why the NH4Cl is made next to the HCl and not next to the ammonia. You need to compare between the mass of the HCl and the mass of the ammonia, and say that this has a larger mass, so the particles will move a little bit slowly, and this has a lighter mass, so particles will move faster. So they are going to meet close to the HCl. And take care, you need to make a comparison between the mass and the movement in order to take the full mark for this particular question. So we have spoken about diffusion in gas. When it comes to the mass of the particle, we said HCl is heavier because it has 36.5 compared with the ammonia, which has 17 grams. So this is heavier, so it's going to move a little bit slowly. And then the second point where we're going to compare between the movement of the gases is the temperature. When we heat the gas, the particle is going to move faster because it's going to gain heat energy, and as the particle moves faster, it's going to collide with more energy, and as it's going to collide with more energy, it's going to bounce farther away, and this is going to increase the diffusion, make the diffusion faster when it's compared with lower energy. In today's lesson, we have discussed the diffusion, we have discussed the kinetic energy, the kinetic theory of substances, and we have seen how a substance can diffuse when it comes to liquid and gas. I hope you have enjoyed today's lesson, and see you next time.